So we're happy to have Sophie Stevens give us an update on the sum product problem.
Cool. So thank you to the organisers for giving me this opportunity to speak, and also for organising these lockdown lectures. I have greatly been enjoying them. So I'll talk today about an update on the sum product problem in the reals, and everything that I say is going to be joint work with Misha Rudnev. And if you're so inspired after this talk, everything that I say is coming from a recent paper which is available on arXiv. All right, so that we're all on the same page, what is the sum product problem in R? So maybe you're familiar with it, maybe it's in the back of your mind, maybe you've never heard of it. So what I'd like you to do, I'd like you to take your favourite set of numbers, so your favourite finite set of real numbers. And if you don't have a favourite set of numbers, I'd encourage your favourite set of numbers from now on to be maybe an arithmetic progression, maybe a geometric progression, maybe just a set of random numbers. So from your favourite set of numbers, now what I'd like you to do, I'd like you to consider all pairwise sums that you can make from these numbers. And you're going to create an associated set, the sum set. So I'll write the sum set as a plus a, and you can play exactly the same game with products. So you can create the product set. Again, I'll write it AA, which is a set of all pairwise products, AB, where they're elements in your set. So maybe the first thing to notice is that, well, the size of A plus A is, well, it's finite, and it's at least the size of your set itself. So you just fix one of these elements, and then the same thing is true for the product set. And the maximum that this can be is, well, you could, in the worst case, all of these can be different. So the worst case that this could be is the size of A squared is the biggest that this set can be. So maybe if you're particularly astute, you'll notice that there's a factor of a half, which I've carelessly thrown away. And this will be a theme throughout this talk. I'll be very careless and neglectful of constants, and always will be the exponents that we get that are going to be the interesting things. Okay, so you've taken your favourite set and you've built two new sets. And the Additive and Szent-Maradi conjecture, so it's a conjecture from 1983, tells you that one of these two new sets that you've built should be big in terms of your original set. So in fact, it should be almost as big as possible. So the maximum of the size of the sum set or the size of the product set should be at least the size of A to the power 2 minus little o of 1. And this little o of 1 term is going to hide lower terms, so lower order terms. It's going to hide constants, but also it's going to hide powers of log A. So also maybe it's worth saying that A is a set, but I'll always say the size of A is A, which hopefully won't get too confusing. All right, maybe a bit of historical background. Additive and Szent-Maradi first conjectured that this should be true over the reals. And they conjectured that if your favourite set with the first n integers, then whatever the size of that product set should be is what this little o of 1 term is hiding. So, I mean, I've said that we're creating the sum set, we're creating the product set, and so real numbers. We can play exactly the same game for complex numbers, and we can say, is it true that one of these must be big? Why stop there? We can play the same game for, well, any setting in which we've got addition and multiplication. And these are just different directions that you can take with this problem. But for the next hour, I will be talking about the sum product problem very firmly, very concretely in real numbers. All right, great. So, this talk is a sum product update. It's a new bound on the sum product problem in the reals. So let's put this in the context where it belongs, and maybe if I were in the advertising industry, this slide might not exist. So what this slide is saying, it's a timeline of the progress that's happened. So time on the bottom, the exponent is at the top, and what's a reassuring thing is that our progress is, our line is going up, our progress is furthered. But there are really two things I'd like you to notice from this slide. And the first thing is what's happening on the y-axis. So the y-axis stops at 1.5. And actually, it the progress stops quite a way before 1.5. Whereas I've said that we expect the exponent, so we expect the size of the sum set or the size of the product set to be going all the way up to roughly the size of a to the power 2. So we expect a 2 to be on this exponent scale. Whereas we're very far from that. So another way of interpreting that is that there's a lot of work that we can still do, and a lot of exciting developments for the future. So the other thing that I'd like you to point out is that in what's happened here, there's two major leaps. Now these leaps I've drawn them in red, slightly bigger, and they represent two fundamentally new ideas in the sum product problem. So the first result is a result of Elekes, and that's this, and Elekes showed that the size of the sum set or the size of the product set is at least the size of your original set to the power 5 over 4. And what was really nice about Elekes' proof is it's in a sense, a 2-3 line proof, and it's introducing instance geometry into the problem. So Elekes used the semi-ready-Trotter theorem to achieve his result of 1.25. And if you've never heard of it before, the semi-ready-Trotter theorem is a theorem which bounds the number of instances between points and lines. So I'll say it in its full, I'll say what it is because I'll use it a lot later. But let's say that we've got a finite set of points and a finite set of lines. Then the semi-ready-Trotter theorem tells you that the number of point line instances, so that's the number of pairs of a point and a line, so that your point lies inside your line, is at most the number of points to the power 2/3 times the number of lines to the power 2/3 plus the number of points plus the number of lines. And again, I've been very neglectful with constants, so there's some constants floating about, but we won't care about that. So what Elekes did, he chose as his point set the sum set crossed with a product set, and chose suitably rich lines to get this result. All right, so this next major leap is a result of Solymosi in 2008, and it achieves a threshold value of 4/3. And this 4/3 is where progress really is. And at a very high level, at a very vague and purposefully vague way, I'd like to describe Solymosi's result as saying that if you've got multiplicative structure on your set of numbers, then you can find a lower bound on the size of the sum set. And I'll leave it at that for now. And then, so Solymosi's 4/3 stood for 3 years, unbeaten until in 2011, Konyagin and Shkredov were able to push a little bit beyond it. So they got 4/3 plus 1/10,000. So this 1/10,000, roughly, arbitrarily, is saying that, well, we can push beyond this threshold. And really every improvement since then, of which there's been these 4, is a refinement of Konyagin and Shkredov's argument, right up until 2018, which is a result of George Shakan, which is the result that we improve. So our result as well, the result of myself and Misha Rudnev, is also a refinement of Konyagin and Shkredov's argument. So Konyagin and Shkredov, they use lots of machinery from different types of maths. So in particular, they use things like semi-ready-Trotter sets, they use the operator method. And what this means is actually that their argument inherits lots of different language from many different types of maths, which means that maybe their argument it's got far more levels of sophistication than it needs. All right, so that brings me to the result of Misha and myself. So that's this final dot. So again, it's quantitatively, it's an improvement, and any improvement is, well, noteworthy. It's a very difficult problem. But actually where the value of our work is refining Konyagin and Shkredov's arguments so that it can be understood at a pedestrian level. And actually that's what motivated us to start this project. It was what's really going on with the previous arguments. Why is it getting a quantitative advantage? All right. And the quantitative advantage that we give is as follows. So for any finite set of real numbers, either the sum set or the product set is at least the size of your set that you started with, so a to the power of 4/3 plus 2 over 1167 minus little o of 1. So if we're willing to believe for a moment that 2 over 1167 is a little bit like 2 over 1000, this is going to give us a bit more ability to compare it with George Shakin's previous result. So Shakin's previous result was 4/3, so the same 4/3 plus 5 over 5,277. So again, very vaguely, 4/3 plus 1 over 1,000, whereas we have 4/3 plus 2 over 1,000. Again, with this little over 1 term. So just to reiterate, this little over 1 term is hiding factors of log a, it's hiding constants, it's hiding lower order terms. All right, so again, this number 2 over 1167, you are now free to forget for the rest of the talk. But what I would like to keep with you is what I'll say next, so which is the proof method. So our proof naturally falls into two parts. The first part is saying that if our set A is multiplicatively structured, then we can extract some information on the size of the sum set A plus A. So in this phrasing, hopefully it's very reminiscent of how I described Solymosi's argument. So what do I mean by multiplicatively structured? By multiplicatively structured, I mean if for every element of A, we've got two associated finite sets, Q and R. So these are finite sets of real numbers. And every element of A has at least T, so T is some number, representations as a product of an element of Q times an element of R. So this little r notation is saying the number of representatives, so the number of pairs of an element of Q times an element and an element of R. So that A equals Q times R is at least T. All right, so that's all very well as half of our proof. So the other half maybe doesn't come as too much of a surprise, but it's saying that every set is multiplicatively structured. So firstly, is this surprising? Well, not so much, because trivially every set is indeed multiplicatively structured. So if I take any element of my favourite set, so this little a, and I multiply it and divide it by another element of that same set, I can write A as AB over B, and I could have done this in, well, as many elements of my set as there were, so in the size of A different ways. So what that means in the notation above is that the number of representatives of my little a as an element, as a product of the product set, so AA, and the reciprocal set, e to the minus 1, is at least however many choices I had, so it is at least the size of A. So even though I've called this trivial, it's kind of trivial because we get it for free, but it's actually, it is a powerful tool, particularly if you know that the size of your product set is small. So we say something non-trivial in the sense that we need to work a little bit harder to get this multiplicative structure. And perhaps at this point you're feeling a little bit uncomfortable because you can see this asterisk here. And you're wondering, is it true that every A really is multiplicatively structured? And well, you'd be right to be suspicious, because what we actually prove is that every set A has a large subset, and this large subset has got multiplicative structure in the way that we want it. All right, so this next slide is for those of you who are familiar with the previous arguments. So again, if you've never seen this before, maybe take a moment just to reflect on the statement of the problem. But if you have seen it before, I've said that my argument, our argument bisects into two parts. So the first thing is if A is multiplicatively structured, we can get information on the sum set. So this replaces Shkredov's, terrible spelling summary, I apologize. This replaces what Shkredov calls sum-ready trotter sets in many of his works. And it replaces bounds on that. And in particular, it replaces the operator method, which Shkredov introduced. And the operator method itself is a beautiful method on relying on linear algebra, and it's lovely. It's too strong for what we need. And secondly, I said that every A has got a large multiplicatively structured subset. And again, if you're familiar with it, this uses Konyagin and Shkredov's bunches argument, or their clustering argument. All right, so for the rest of this talk, it's kind of going to bisect naturally into, well, I'd like to talk about how I get this result of what does it mean if A is multiplicatively structured, to get some information on the sum set. And then once we've covered that, we'll talk about how to find the subset, which is multiplicatively structured and why it is multiplicatively structured. So this seems like a good moment for a pause in case there are any questions. Great. All right. So our aim for now is going to be to show that if we've got multiplicative structure on our set, then we've got some additive information. So again, this multiplicative structure, we're going to suppose that every element of our set A has got at least T solutions to the equation A equals QR. So that's just written this next line in a different way. Then the size of the sum set to the power 19 times whatever this Q is, the size of that to the power 22, times the size of R to the 22, is at least the size of A to the 41 plus some factors of log A times this number T to the power 33. These are some quite bizarre exponents. We don't believe that these exponents are the correct ones. We believe that this theorem can be improved, and were it to be improved, it would give quantitative improvements on the sum product problem. And maybe another remark that's worth saying, this theorem, as stated in the context of this talk, is over the reals, but actually the proof of the theorem is valid as well, just for complex numbers. All right, so multiplicative structure gives us additive information. So why is this? So I've kind of hinted towards this. I've said that this replaces Shkredov's sum-ready trotter sets idea. And indeed, we will be using the sum-ready trotter theorem to use the fact that we've got multiplicative structure, and it's going to give us some good additive information. So it's going to give us additive information in the form of additive energy. So the additive energy between two sets, if you've never seen it before, so let A and B be some finite sets, let K be any number bigger than 1. Then the kth energy of A and B is somehow the kth moment of the representation function of the difference of A minus B. So what we're going to do, we're going to look in the different set A minus B, we're going to look at an element there, and then we're going to ask how many different ways can it be written as an element of A minus an element of B. That will give us a number. We'll look at that to the power K, and we'll sum over all elements of X. All right, and if we've got multiplicative information on our set A, then we can estimate this quite well. So let me give you a hint as to how this happens. So let's look at the support of this function. And let's look at elements of the support which admit many representations. So I'll introduce a parameter tau. And so we're going to look at x tau, which is going to be the number of is going to be the set of elements in the support for which this element x can be written as A minus B at least tau times. So on the one hand, if we were to look at the equation x equals A minus B, where these variables live in the relevant sets, then by my definition of x tau, there's at least x tau times tau solutions to this equation. So any x that I pick has got at least tau pairs A minus B. And then on the other hand, I know that A is multiplicative. I know that A is multiplicative in the sense that A can be written as Q times R at least T different ways. So I'm now going to use that information. I'm going to replace A by Q times R. And because I've overcounted now, I could have done this T different ways. I need to compensate for that by dividing by T here. All right. So we now don't have to look very hard at this equation to realize it as a point line instance. So maybe we'll take as our lines with slope Q and y-intercept minus B, and our points R cross X. And this is great because this means that we can use the Semredy-Trotter theorem to bound this right-hand side. And I've said that the Semredy-Trotter theorem is an instance bound between points and lines. It's kind of not important what the actual numbers are. Well, I mean, it is for quantitative things, but for why this works, it's not so important. But because of the quantitative form of the Semredy-Trotter theorem, it means that this trick is really good for any k, so this kth moment between 0 and 3. So there's a few technical details I've swept under the rug there, but not too many, and I'm very confident that all of you, given half an hour, would be able to fill in all details, regardless of how familiar you are with this. All right, so if we've got multiplicative structure, then we can turn this support into a point line incidence, and we can bound it. Okay, so let's return to the theorem that we'd like to prove. We're saying that if we've got multiplicative information, then we've got this lower bound on the sum set. And let me prove it in a really toy case. So I'll make it clear at which point I'm really assuming a model setting. So firstly, let's look at the difference set, A minus A. And let's suppose that every element of our difference set has got, can be written as A minus A the same number of times. So every element can be written, every D can be written as A minus A at least, well, exactly delta times. It's a model, why not? If this were true, then delta would turn out to be A squared over A minus A. Okay, and then we're going to ask the following question. How many solutions are there? So how many variables A, B, and C, all living in our favourite set, are there to the equation A minus B equals A plus C minus C plus B? So this is kind of a stupid equation. So on the one hand, there's lots of solutions. Any A minus B, any A or B that I pick, I can always find a C for which this is true. All right, so there's at least, well, A minus A. So I'm going to count the solutions in a weird way. So there's at least A minus A, so the number of left-hand side choices. So I'm gonna pick an element for the left-hand side. That's going to give me this A minus A. My left-hand side could be written as A minus B, at least, well, delta ways. And then I was free to pick C, and C just lives in A. So on the one hand, I've got at least delta times A minus A times A solutions to this equation. And I've written the number of solutions in this convoluted form so that if we were to go from the model case or to reality, it really is, this is how we're counting it. So on the one hand, we've got this lower bound for the number of solutions. So what we'd like to do now, we're going to partition the solutions into equivalence classes. We're going to say that if we've got a solution A, B, and C, then it's equivalent to another solution, say A prime, B prime, C prime. If, well, A minus B is the same as A prime minus B prime, if A plus C is the same as A prime plus C prime, and if C plus B is the same as C prime plus B prime. So every time I've got a solution, I'd like to partition it according to what values it takes for each of these summands. And it turns out that this is the same as partitioning solutions into equivalence classes via this translation that I've written here. Okay, so then we're going to count the number of solutions. So we've counted it in one way, and we're going to count it in another way. We're first going to count over the number of equivalence classes, and then the size of each equivalence class, which, after the Cauchy-Schwarz inequality, tells us that the number of solutions has as an upper bound the square root of the third moment energy of A times this rather complicated looking expression. And if you'll remember back to a slide ago, I said that we're actually, because we've got this multiplicative structure on our set A, we're really good at estimating E3 of A, or in fact any EK of A as long as K is less than 3. So we can kind of disregard this first term as something that we understand and we can bound well. So let's look at this rather more complicated expression. So again, I've just written out here, how many solutions are there to this? So I've imposed the first model. So this first model was on the representations of D. I'd like to impose a second toy case onto this. I'm going to suppose that, say, every X here has got rather a lot of representations as an element of A plus A. So the average number of representations would be, if we're in a really equal case, the number of representations would be A squared over A plus A, and let's give ourselves a bit more leeway and get this factor of 2. So every X that I end up with here from my equivalence class is rather popular. Okay, so this means that when I'm counting the number of solutions to S, I can play the same game as I did earlier. I've got D equals X minus Y. I know that X looks like an element A plus B at least this many times. So let me do that and then compensate by dividing by this number. All right, which gives us again something that we understand plus a slightly more complicated expression. So this slightly more complicated expression, D equals A plus B minus Y. So D and Y live inside these sets, A and B live inside the set A. It's precisely the number of equations, the number of solutions to the equation D minus B equals A plus Y, which, I apologize for the forthcoming typo, is another way of writing this. It's a number of, it's summing over X and counting the number of ways that X can be written as the left-hand side, and this should be an X, times the number of ways that X can be written as the right-hand side. All right, so we've got we've got a sum over a product of two complicated expressions, which we don't really understand combined, but maybe we would understand them if it was separated, which means that this is a perfect candidate for an application of the Holder inequality. So we'll do that, we'll separate out these two terms, and we'll use a third Holder inequality, which is going to give us e to the 3/2 energy of this first term, and then we'll have a third energy on the second term. And again, remember, we've now got some energy equations. Each of them involve our set A, and our set A has got multiplicative information, and each of these subscripts is less than 3, which means that we are in a great position to bound them efficiently. Okay, so if we were now just to run over all the calculations that I've talked through, that would give us the theorem in this model case. However, I have cheated slightly when talking to you, and I've imposed two models. So let me kind of describe how to go from, well, the world in which we live to these two toy models. So in the first toy model, I said that every element of a different set has got the same number of representations. So actually getting rid of this model isn't particularly difficult. We apply the dyadic pigeonhole principle. So that is, we're going to partition the set A minus A into subsets, so that for every D inside each subset, there's between, say, delta and 2 delta representations. This is going to cost us a logarithmic factor, which, when you rearrange, gives us a product of logarithmic factors. But I said that we only care about the exponent, so we're happy to pay that price. The second model case that I imposed was saying that when I was looking at my equivalence classes, every X which lived in the sum set was popular. So this isn't quite true. It's a bit too much to ask that X is both popular and also, so it's a bit, X interacts with this set D that we find here, or this subset of the different set that we find here. And for this, we apply a new regularization lemma, which I won't talk about, but I will just say that by applying it, we can ensure that this element X is as popular as we need it to be, as long as we're willing to weaken our condition of popularity. And also, the second point is really saying it just interacts well with this different set as we want it to. All right, so this actually concludes proof of the first thing that I wanted to tell you, which was saying that if we've got additive energy, multiplicative structure of our set, then we've got a lower bound for additive energy. And actually, all we really used is the fact that we can estimate energy well if we've got multiplicative information. But there's actually a whole family of sets for which we can estimate energy well. And this is convex sets. So a set of real numbers is said to be convex if we line them up and if we order them and we look at the consecutive differences. These consecutive differences always grow. And for convex sets, so if A is convex and X is an arbitrary set, we can estimate E of S well. And this comes from the Solymosi theorem. So it's the same trick that we used before, except, well, okay, it's not the same trick that we used before, but it's a really similar trick that we used before. And this allows us, by just repeating this whole proof that I've just gone through for convex sets rather than for arbitrary sets, to improve previous best bounds. The previous best bounds are a really recent result of Olmazov, which is saying that the sums of convex sets, the number of sums of convex sets is at least the power of 8 at the 102 over 65 multiplied by 1, 230 over 19. So we'd kind of expect for convex sets to have maximal sum sets. So we'd expect to get a 2 here. Whereas here we're doing 30 over 19 is better than what we've got for some product, but again, still quite far from 2. And it's interesting to know, well, it's at least interesting to me to know that if we were to replace our quest for the number of sums of convex sets to instead the number of differences of convex sets, then we improve it here to 8 over 5, which would be noteworthy if that weren't already known. And that's this 8 over 5 for differences is something which has been known for many years. I'm trying to think then how many years, and it's a result of Konyagin and Shkredov. So we can match their result, but we can't improve it, which, even though we're using a different technique, is, I don't know, quite interesting. It really is a threshold bound. All right, so I think this concludes what I wanted to say, that if we've got multiplicative structure, then we know something about the sum set. And again, I'm going to take a moment just to pause to see if anyone's got any burning questions that they'd like answered or clarifications.
Yes, Sophie, in this multiplicative structure implies additive information theorem with all the different exponents in it. Have you got a feeling for what the truth should be there, and you know what would be the best corollaries of an optimal result? You know, how far could what's the best result you could get in terms of some products if you had the best possible result in this situation? Have you thought about that?
So we have a bit. So the best, to answer the first question, the best possible thing that we could hope to get for some product using this is 3 over 2, which is the next fraction to come up with. I don't think we can beat 3 over 2 with this, but I'm willing to be proven wrong. And so I think we have thought about what the best version of this would look like. And, let me think. So these powers of 22 and 33 remain in this best version, but there's 19 increases and there's 41 increases. And our intuition from this came from, not quite sure if it was conjecture of George Chapin or just a hope that he expressed. But if you unpack his notation, translate it to our notation, it gives you what this would be, which unfortunately I've not got written down to hand. But if someone is interested in that, feel free to email me and I will dig out that calculation of the past.
Thanks.
All right. So I said that if we've got multiplicative information, then we get a lower bound on the size of the sum set. So my second claim is that every set A has got a multiplicatively structured subset. Okay, so what I'm going to do for the remainder of the talk, I'm going to say how to find this subset, and then I'm going to justify very loosely as to why this is as to why we get the data that we then feed in.
We have a question in the chat.
Please.
So if A is convex, do you expect that the sum set has size, at least size of A to the 2 to the minus little of 1?
I think that is what is expected. The reason I've not written it down is because I couldn't find that in print, so I'd be interested in the reference if anyone has it, but I think that is what is expected. And again, the same for the different set. All right, so return every A has got a multiplicatively structured subset. So again, I'll say how to find the subset and then I'll justify why it's multiplicatively structured in the quantitative form that I claim it will be. And one of the nice things about this argument is that it's entirely pictorial. It's almost entirely pictorial. All right. So every A has a multiplicatively structured subset. If you've seen the sum product problem before, you won't, it comes as a surprise as the first thing that we're going to do is we're going to look at a point set, A cross A, and we're going to cover it with lines through the origin. So all of these lines will have slope in A over A, so this ratio set. And I'm going to assume a toy case. And the toy case I'm going to assume is that we've got the same number of points on each line. In this toy case, the number of points on each line, I didn't write, but I'm going to think of as tau. And if I think of the number, this means that the multiplicative energy in this toy case is the sum over lines, and then for each line, I'm going to look at the number of pairs of points on that line. So if I've got, say, S slopes and tau points per slope, the additive energy in this model case is going to be, the multiplicative energy in this model case is going to be S times the size of S, so the size of the number of slopes, times tau squared. All right, we don't need to know this. Okay, so now that I've done this, what I'm going to do, I'm going to look at each possible x value that these points can take. So I'm just going to go through every element of A, lying on my x-axis, and I'm going to look at the vertical line through that point. And what I'm then going to do, I'm going to count the number of intersections between this vertical line and the number of points of A cross A. And I'm going to do this across each possible x value. And one of these x values is going to give me the most number of points. So I apologise if you're colourblind, but what this means in terms of this picture is I'm going to go along the x-axis and look at vertical lines. I'm going to count the number of green points on each line that I get. One of these vertical lines is going to have the most lines, and it won't necessarily be unique, but it'll exist. We'll just pick one that has the most lines. Okay, so once I've done that, I mean, there's clearly space for one more picture. And there's kind of only one thing that we can do to find this subset of interest. And that's, well, they've all got the same x value, these special points. Let's look at their y value. And let's choose this y value to be this special multiplicatively structured subset. Okay, so hopefully it's clear what this multiplicatively structured subset is. Maybe a question that maybe that should be on your mind is, why is this multiplicatively structured? So why is this subset special? So let's look at any element of this subset, so any of these y values. Let's look at B4. What does B4 look like? B4 looks like some slope, so some lambda times this x value, some lambda times x is 0. Now, remember this toy model that I imposed. I said that every slope has got tau points on it. So what that is saying is that I could write lambda as a1 over a2 tau times, which means that, well, if I fix b, x0 is kind of automatically fixed from my definition of b. There are tau solutions to this equation. So tau solutions, there's already quite a lot of solutions. We can play our favourite mathematician trick of multiplying by 1. And we can bootstrap this argument to get that b equals a1c over a2c times x0. He's got even more solutions. And I'm going to be a little bit particular, and I'm going to insist that my element c that I've arbitrarily multiplied by 1 with lives inside my set A, so the big set. All right, so now we're going to ask, how many solutions are there to this equation that I've written? Well, the number of solutions is well, captured by the number of, say, denominators to this equation. So what we're actually going to ask is, how many denominators are there to this thing that I've written? So what I'd like you to notice is that A2, this element A2, lives inside A. And by definition, because, well, A1 over A2 equals lambda, it means it also lives inside this dilated A. So it lives inside A, and it lives inside a bigger set, but their intersection is somehow special. This means that every denominator is going to live inside the product set, but also this smaller, this other set. Okay, so this might not actually seem groundbreaking, but this is one of our quantitative improvements. So previous iterations of this argument, so even including Shaken's argument, used the fact didn't multiply by a c in A, but multiplied by a c in A lambda, which means that the number of denominators is far smaller than what we've got here. So again, it's a very elementary, very simple, but it's worth pointing out this is one of the quantitative advantages that we get. It's all right. So what this means, what I've written here, is, if you remember back to the notation of previous slides, saying that every element B looks like, well, a dilate of the product set times 1 over the product set at least this many times. Which is pretty good news for us, because what we'd like to do is have a set for which we've got this multiplicative structure, and then we can just whack it in. So when we use this data, when we apply this data, we're actually going to apply it with our subset B. So we're going to get b plus b to the 19 times the size of the product set to the 22 times the size of this product set to the 22 is at least the size of b to the 41 times whatever this number is to the power 33. So I've not actually told you how big b is, and that's because we're in the toy model. So maybe it's worth just saying that the size of b is related to the multiplicative energy of A. All right. The final ingredient of our proof. How big is this number? How big is this t that I'll put in? Again, it's pictorial. And I've been talking for a long time, so maybe before I try and convince you how big this is, I'd like to promote the fact that how big it is an elementary argument. It's an argument that is not it's not simple. It's not what you expect a kindergartner to be able to do, but it doesn't use any particularly deep results. In fact, the deepest result it uses is the Semreni-Trotter theorem, but a version of the Semreni-Trotter theorem which admits an elementary argument. So it's a really combinatorial argument, this. And that's the same again for our whole paper. All right, so we've got A and we've got A lambda. How big is it? So we're going to look at this very familiar picture again. Here I've not assumed a toy model. And we're going to assume that A times A is covered by lines through the origin. So each line, again, has got slope in A over A. Now we're going to apply the dyadic pigeonhole principle. So this is, in general, how we go from reality to simplify to our toy model. So what we're going to do, we're going to look at each slope. We're going to partition our slopes according to the number of points per slope. And we're going to say that, well, there'll be one set of slopes for which the number of slopes times the number of points per slope squared. It's all written down, so you don't, I apologise, represents the size of the multiplicative energy. And let's just remember, the multiplicative energy is number of quadruples, pairs of which share the same slope. Okay, so far I've done nothing. Okay, so this is maybe where it starts to get familiar if you've seen Konyagin and Shkredov's argument. So what we'll do now, we'll partition the slopes into bunches of size n, the sum parameter n. And again, it should be looking familiar if you've seen this argument before. Within every slope, we're going to create all possible vector sums from points lying on different lines. So in particular, we're going to create the sum A and then say lambda 1A, this will be the slope lambda 1, and then B and lambda 2B. So again, this is nothing new. This is the foundation of Solymosi's argument, is the fact that this new vector sum that we've created lives inside the sum set A plus A cross the sum set A plus A. Maybe something to notice, this little a is, by the notation of earlier, an element of A sub lambda, which is quite good for us because we like to get a bound on something involving that set. All right, so here is where our argument differs from that of Konyagin and Shkredov and subsequent arguments. So Konyagin and Shkredov then counted how many times the arguments may collide and arranged their bunches so that not too many of them did collide. Whereas what we're going to do is kind of in some sense the opposite. We're going to say that some new elements may collide, and just let's take a moment. If some elements collide, that's saying that we've got some 4 points within the same bunch, so that the sum of, say, A1 lambda 1 plus B lambda 2 is equal to the sum of, well, the other two. So we've got this pattern appearing. And let's for a moment just fix our lambda 1, lambda 2, lambda 3, lambda 4. So a collision, so this is a simultaneous equation. Once we've rewritten that, a collision is saying that we've got a fixed lambda, so the lambdas become these constants. We've got a solution to this equation. So where each of the A lambda i's live inside the set A lambda I. So that's the set A intersected with lambda I to the minus 1 times A. All right. So this is already, again, at each step, it's nothing hard, but it's a lot to keep in your mind. So I'm not going to go too much more into the technical calculations of it, but I would like to run you through the idea. So we're going to choose n so that we've got lots and lots of collisions, and n's a parameter, remember, so we can do that. So if we've got lots of collisions, that's saying we've got lots of solutions to this equation. So we've got lots of solutions to this additive equation. And in fact, this is actually the form that we need to get a few sums, many products type result. And this is maybe, I guess, classical, a result of Elekesh and Ruger, which we can use as a black box, or we can, again, reprove it in an elementary method for our purposes. And what the result of this is saying that the multiplicative energy of A lambda is small. So this is great for us because what we'd like to bound is A times A lambda, to which we can now just apply the Cauchy-Schwarz inequality. If you're familiar with the Cauchy-Schwarz inequality, this will tell you everything. If you're not familiar with it, this isn't going to enlighten you, so I'll just flash it up here. All right, so this gives us a bound of A times A lambda in terms of quantities that we understand. Okay, and that brings me to the end of our proof. So let me just take a moment to recap what we've done. So our aim was to find a new bound on the sum product problem, so 4/3 plus a bit. And we did this in two parts. We said that if our set is multiplicatively structured, then we can use this multiplicative structure to apply the Semeredi-Trotter theorem. And with the Semeredi-Trotter theorem, we can bring in efficient additive energy bounds, giving us information on the sum set A plus A. And finally, we said that every A has got a multiplicatively structured subset. And we found this subset by just looking at the abscissae of points of A. And we argued that using few sums, many products, this multiplicative structure is as quantitatively as we need it to be. So in a sense, this second part, I don't know, maybe it can be improved, but it's not so obvious to me that it can be improved. I'm not willing to claim that it's best possible, but this first part, it really can be improved and really would give stronger quantitative bounds. So that brings me to all that I wanted to say, and I'm very happy to take any questions that you might have. Thank you.